In this video, we are going to start with non-ordered data structures that include sets, maps, and hash tables. So far in this course, we have discussed different linear ordered data structures that include lists, stacks, and queues, and non-linear ordered data structures that include trees. Now we are going to discuss non-ordered data structures, which basically are mechanisms to store data which do not have some inherent ordering. We are going to start with sets in this video, and in the next video, we are going to talk about maps. In the next lecture, we'll also discuss the implementation of these sets and maps using something called hash tables or this entire technique of hashing. So let's get started with sets. Sets in the context of computer science are pretty similar to what you might have already seen in your high school, in your algebra, or in statistical classes. A set is basically a collection that contains no duplicate elements. So you can think of set as a box, and this box could have like integers, it might have strings, it could also have maybe objects, or it could have a combination of all of these. All these elements or these set objects, as we call them in computer science, they are not indexed, which is in when we talked about like lists or other data structures like representation of trees, we discussed that like if we do something like arr of I, we can retrieve a value, but since sets element are not indexed, so we cannot do something like set of I or set of j and so on. Also, they do not reveal the ordering of insertion of items. And what I mean by that is, let's say if there are two elements in the set like 1 and 2, we do not know whether 1 was inserted first and then 2, or whether 2 was inserted first and 1. It is completely specific to the implementation, and we might not be aware about whether how the set might be implemented behind the scenes. What we truly care about is what is the functionality that is offered by this set data structure. Another thing to note here is that sets enable efficient search and retrieval of information. That's why they are such an important and fundamental data structure, because they do allow us to search or find elements in really fast execution times because of this concept of hashing, which is like we'll see one way of implementing sets as hashing in the next lecture. But I'm just giving you idea that you can retrieve these objects in O of one time. Because earlier when we saw, like let's say if we had the sets in the form of arrays, we required like O n in terms of linear search or O of log n in terms of binary search. Or when we implemented like trees, we also saw the best we can do to find an element is like O of log n. So sets are a way much more faster than all the data structures we have seen so far. The final thing is they do allow removal of elements, which is you can remove the elements without the other elements moving around, which is if we remove like 2, 1 and 3 don't know whether 2 was removed or not, or like it's not available up to the user to see what's going on behind the scenes, but they can easily remove elements. So here I've taken a set of fruits that contain lemon, strawberry, grapes, pineapple, peach, apple, pear, and banana. And we are going to see the set again and again because I'm going to show you like how the different functions look like when we talk about the set API. So let's talk about the set abstract data type, or the API that is provided by the sets in general. So in the context of computer science or even mathematics, the ADT supports the operations which is generally available in mathematics. The first one is testing for membership, which is like, let's say if we had this set, can we find like an apple in this set or not? So in this case, the find method in C++, which is like specifically about C++, will return an iterator to whatever we are trying to find and will return null if that element is not there in the set. So let's say if I try to find apple, I'll get an iterator back to apple. or where it is pointing to in the set. And if I try to find, let's say, a kiwi, since it's not there, I will get a null value. The next one is adding, which is just to add an element in the set or insert an element. The next one is removal, which is to remove an element from the set. Now, these operations are fundamentally available in all the different languages that I know, like Java, Python, C++. These ones are specific to some languages, like some languages might have them, otherwise you need to implement them. So like union and intersection, you do not have a way to do that in C++. The C++ STL doesn't have those operations. But you should know like what is union intersection difference between two sets, as well as what is returning a subset means. So I'm going to discuss each of these operations because let's say in the exams or stuff, you might be asked like implement, how would you find the union of two sets? How would you find an intersection of two sets? Given you are implementing like each set by one of the mechanisms we are going to discuss uh, in the upcoming slides. So let's talk about these other operations. When we talk about union of two sets, union is operation is basically the a set whose elements belong either to A or B or to both A and B. So what we basically do is we find out what are the elements that are in set A and set B, and we sum them up in the final set, which is this is A union B. Now, by the property of sets that it cannot contain duplicate elements, all the similar elements, like in this case, lemon is in both sets, so there'll be only one copy in the final set. When we talk about strawberry, there's only one strawberry, it's not in B, but it's still going to be there. Next, we have grapes. So we add grapes in the final set. And then we have an apple in set B that's not in A, so it's in the final set. The next operation is intersection. So an intersection operation allows us to find all the elements that are in both sets. So this is set A, this is in set B. We are going to see what are the common elements in both of these sets. So in this case, lemon is the only one because strawberry and grapes are not there in both of these sets. So finally, we have A intersection B, like A intersection B is denoted by this symbol, while A union B is denoted by this U symbol, will contain this lemon object. Next, we have this difference operation. So in case of two sets A and B, and if we want to find what is the difference of two sets, the final answer will contain all the elements that are in A but not in B. So lemon is in both sets, so they do not satisfy this condition. Strawberry is in A but it's not in B, so it will be in our final answer. Grapes is in A but is not in B, so it will be in the final answer. And when we talk about apple, that's in B, like we do not even have to think about what's there in B and so on. So A minus B will have all elements that are in A minus whatever is repeated in set B, which are already there in A. So the final operation is set A is a subset of B, and this is denoted by A is a subset of B. In this case, every element in set A will be in set B. So in this case, you can see lemon is here in set B, strawberry is here in set B, and grapes is here in set B. Let's say if I had another kiwi, then we would denote these two sets as A is not a subset of B. So now let's talk about what's the difference between lists and sets we have seen so far. So when we talked about lists, they had some inherent ordering, which is the elements were ordered one after another, whether it was a linked list or whether it was an array. And you can easily say that, okay, this element A might be inserted after B or before B, or like C would be after B or before C or something like that. But in sets, since there's no inherent ordering, we do not know which element was inserted first and so on. Next, when we talk about duplicates, lists can contain duplicates while sets cannot. Finally, when we talk about implementations, we discussed that list ADTs, which we discussed in our second week, can be implemented by arrays or by linked lists. And when we talked about linked lists, there were different ways that you can implement linked lists that include like single, double E, circular, and so on. Sets are typically implemented in two broad categories. The first one is array-based set, and the second one is tree-based set. So when we talk about array-based set, it is so trivial that we are not going to discuss it again, which is like if you have some fruits, you insert apple into this array, and then you add maybe mango, and then you add, let's say, uh, banana. If you implement the set in the form of an array, and then if you implement the find operation, you can do a linear search on this to find whether the element exists or not. Now, since like the designer might be able to implement a sort function as well and keep it sorted, and then you can implement the find using binary search. But the user, which is the person who's calling the functions, he or she doesn't know whether they have sorted the elements are sorted or not. So this is one important distinction that you need to make sure. Like, we do not know how it might be implemented, we just care about the functionality. It's just the nature of true abstraction in computer science. Tree based set have like sets that are implemented as trees. So here now apple could be the starting one, and then you can implement this maybe like a bst, and then you can have mango, so you can push that, and mango goes towards the right because m is greater than a. And then we have banana, so it goes towards the left of mango, and so on. So let's talk about sets in C++ specifically. So the C++ standard template library, like, you can always implement your own sets and maps, but since they are already implemented in the standard library, we want you to be very comfortable with how to use sets and different map data structures to actually solve problems rather than like reinventing the wheel. You might have like a question or two like how to implement them, but we also want you to be very comfortable with the how to use sets specifically in C++ using the STL. So STL in C++ has two different ways of implementing sets. The first one is called an ordered set, which is defined as std set, and the other one is std unordered set, which is a set that actually implements behind the scenes hash table. So kind of like unordered set is the true set in C++ because it has like one time complexity for different operations, while the this set is actually a tree based set, which is similar to what you have already seen. Like, we have already covered trees, so you are implementing tree behind the scenes. Now, there are some pros and cons of both approaches. In the tree-based set, the elements are sorted because if you are implementing, let's say, some form of BST behind the scenes, if you do an in-order traversal, you can get the sorted list of the elements in the set. Typically, this is actually implemented as a self-balancing BST, which is like a red-black tree behind the scenes. While when we talk about unordered sets, the elements are not ordered, which is we do not know whether they are how they were inserted. So these are like true sets, how we can see in statistics. Now, the time complexity for various operations in case of a tree-based set is typically O of log n, because when we discussed like red-black trees, we discussed that most operations like insertion, deletion, or search have typical complexity of O log n, which was something around 1.44 log n. Next, the unordered sets typically have the time complexity of common operations as O of 1 plus O of k for like large hashes, but since k is a very small number, this is typically ignored. The terminology, you won't be understanding what a hash is and stuff till the next lecture, but behind the scenes, it's implementing a hash table. So we are going to discuss that very soon. Here the implementations is like a BST I just explained. Now the initialization, how to initialize sets in C++ is just using the set type and then you can use some name like S. While an unordered set, you have to use this full convention, which is unordered underscore set, followed with type and then the name of the set. The common operations that are associated with the tree-based set include insert, erase. So insert just inserts an element, erase deletes an element, find finds an element, which is whether there's a pointer or not to that element. Count finds whether the element is there along with its count. So since we know that sets typically have either 0 or 1 elements, like it cannot have more than one copy of the element, this number will always be either 0 or 1. Size will return the number of items in the set, and empty will return whether the set is empty or not. So all these operations are similar in these two. Also, the unordered sets also have some other methods that include like bucket size, load factor. You won't be able to understand these methods right now, but once we start discussing hash tables, then you'll understand the true meaning of what is a bucket size and what's a load factor. So I'm not going to discuss it here, but I'm going to discuss that very soon in the upcoming video. And then we are going to visit these sets and maps again. Also, the references for the common methods are shown here. Like you can go to this website. It's a really great reference website. It has all the operations. So I've just included common methods, but that's not an exhaustive list. There are much more methods apart from this. So let's see a quick example of ordered and unordered sets in C++. So here I have an ordered tree-based set of integers. Now I'm inserting 5 into the set, then 2, then 4, and then 11. Now when I insert 2, since 2 is already there in the set, the value will just be overridden. Now, if I want to iterate over the set, you can use like auto and then itr1 and then print it, or you can use like the actual data type, which is set int and then followed with iterator. You define an iterator, iterate over the set, print the elements, and you can see here one important distinction, that since the set was ordered, when we print it, it will always be in sorted order by default. So behind the scenes, like this set is implementing a red black tree. And if you do an in order traversal of a red black tree, you'll get an ordered, a sorted list of numbers. So that's what's happening behind the scenes. When we talk about unordered sets, we define it using this convention. So this here you can define a type. It could be anything, like we are just using templates. Next, I insert like 5, 2, 4, 11, and then when I insert 2, since it's already there, nothing happens. Just the same convention for both the sets, but like different ways of implementations, which is calling either a set or an unordered set. So you might think that if this is O1 while this is O log n, why would we ever need a tree based set compared to a hash table based set? So there might be cases where we want to keep our data sorted, and in those cases this form of set, which is the regular set in C++, might make more sense when compared to the other one, because when we study these unordered set, we are going to study that they take more memory, while the regular sets consume less memory. And it's a strict trade-off between memory and time, because in this case, since they have less memory, they take more time, while since they have more memory, they take less time, and so on. These things will again be clear once we talk about like what are hash tables. Okay, so here again I have an iterator, I print the set. Now you see that the numbers are not ordered, which is 11, 4, 5, 2. We do not know how it's sorted. Maybe sometimes you'll get a list that's sorted, but that doesn't mean it will be sorted. It was just out of random based on our hashing function of the hash table. I'm also printing out some other values, which is like the bucket count, load factor, and max load factor. We are going to discuss that in the next set of videos, and we are going to come back again to what these numbers or values actually mean. In the next video, we are going to talk about maps. Thank you.